Welcome back to Hypnosphere. This is a quiet place for unhurried science, where we let big ideas open slowly, like eyes adjusting to starlight. If you are new here, I am glad you arrived. If you wish, you can write in the comments where you are listening from, and what the time is for you right now. Tonight we will stand near the most mysterious structures the universe has to offer, and we will ask a childlike question with adult care. Could black holes be gateways? Not only gateways in the adventurous sense of tunnels to distant places, but also gateways in the quieter sense, doors that open onto new kinds of understanding. The word gateway can mean a passage to somewhere else. It can also mean an entry point into a deeper theory. Black holes invite both readings. They are practical, real, astrophysical objects that bend starlight and drive the dynamics of galaxies. They are also conceptual pressure points where gravity, quantum mechanics, thermodynamics, and information meet. If there are secret hallways in our physical laws, the handles may be embedded in these dark wells. Take a moment to picture one. Not the violent, dramatic versions from films, but the patient object that sits at the center of our own galaxy. A dark circle against a glowing ring, teased from radio waves by the Event Horizon Telescope. Around it, gas orbits and heats, and in that heat are magnetic fields, and in those fields are structures that twist and flare. Behind it is the glow of the sky. In front of it is us, holding together a picture made by instruments that span the Earth. The black hole itself is simple to describe. It is a region of space-time from which nothing, not even light, can escape. The boundary of that region is the event horizon. Inside, the known laws say that gravity crushes matter to a point of infinite density called a singularity, although many physicists expect that the singularity is a signal that our equations are incomplete at extreme conditions. Black holes form when enough mass is squeezed inside a critical radius. In nature, the squeeze happens during gravitational collapse, when a massive star burns through its nuclear fuel and the outward pressure that held gravity at bay disappears. The core falls inward. The outer layers explode in a supernova, and if the mass is large enough, the remnant continues to collapse past every hope of escape. Binary black holes can form as pairs of massive stars age together. Supermassive black holes sit at the centers of most galaxies, millions to billions of solar masses, their origins still being traced through mergers, accretion, and the history of the early universe. The word portal is tempting, but we will be careful. We will separate what is known from what is hoped, and we will keep a gentle floor under speculation. There are at least 3 senses in which black holes could be called gateways. First, in a purely geometrical sense, the mathematics of general relativity allows for spaces that look like bridges, joining one region of spacetime to another. These are wormholes, and the idealized bridge that appears in the extended description of a non-rotating black hole is an example. Second, in a quantum sense, black holes may be gateways for information, not to nowhere, but through subtle channels that carry quantum correlations across horizons and back out again, restoring unitarity and reconciling thermodynamics with gravity. Third, in a human sense, black holes are gateways into new thought. They press our most tested ideas to their limits, and in doing so, they reveal how those ideas need to be completed. Our journey will move between sky and theory. We will visit early imaginings of dark stars, the crisp geometry of Einstein's equations, the patient fieldwork of observers who watched X-rays flicker and gravitational waves pass through the Earth, and the quiet audacity of proposals that invite negative energy and quantum entanglement to hold open a throat in spacetime. We will let metaphors help us, but we will keep them tethered. We will not hurry to pass through any door. We will spend time at the threshold, learning what the doorframe is made of. For a moment, notice your own body as a small gravitational system. You are held to Earth by a field that you cannot see, but that you can feel when you climb stairs or lift a bag. You are watching a screen that emits light, and your eyes are tiny telescopes that catch it. Somewhere inside your mind is an intuition that black holes are places where gravity is simply stronger. This is true, but incomplete. Black holes are not only strong gravity, they are places where the very geometry of space and time becomes different, where the ordinary notion of inside and outside, forward and backward, can confuse us if we carry them too far. In some coordinates, time and radial distance swap roles inside a black hole. That swap is a hint that the interior is less like a room, and more like a path with a destination that cannot be avoided. Understanding this already feels like a gateway, a passage from everyday vocabulary to spacetime's grammar. There is a tender aspect to this topic. Gateways can be symbols of loss and hope. Black holes meet both. Stars die to make them. Galaxies are shaped by them. They are engines of some of the brightest events we have seen, not because of their own light, but because the matter that spirals in can be whipped into jets that span hundreds of thousands of light years. In their shadows, we glimpse our limits. In their mathematics, we glimpse the chance that limits are invitations, not walls. As we begin, loosen the grip of sci-fi. Keep the wonder, soften the urgency. We will not try to rush through an imaginary tunnel to another universe. We will learn what the tunnel would have to be, and what energies and symmetries would have to cooperate to make it safe for a traveler. We will ask whether nature provides those conditions on its own, or whether wormholes are more like laboratory dreams, possible within carefully crafted cages of negative energy and quantum control. We will consider loop quantum gravity's proposal that a collapsing core may bounce into a white hole, a kind of explosion in slow motion that returns matter after a long delay. We will look at string theory's suggestion that space-time might be woven from entanglement, so that a pair of black holes connected by quantum correlations could be considered two mouths of a bridge. We will keep a light, steady hand on each line. At the edge of the horizon, time slows. For an outside observer, a clock falling toward a black hole appears to tick more and more slowly as it approaches the boundary, red-shifting until its signals fade into silence. For the clock itself, nothing special happens at the horizon. It crosses in finite proper time and continues toward the interior. Two perspectives, both allowed by the same geometry. When people speak of black holes as gates, they sometimes forget that the horizon is not a physical surface, not a wall you could touch. It is a global property of the spacetime, defined by the fate of light-like paths. To know whether you have crossed it, you must know where light can go from your location. That knowledge is not local. A gateway that cannot be seen from up close is a different kind of door. This difference will help us keep our balance. Here is the rhythm for the night. In a moment, we will step back in time to when thinkers first imagined stars so dense that light could not escape. We will watch how that idea was set aside, then rediscovered, and how it grew into the precise concept of an event horizon. Then we will look again at the sky, at X-ray binaries, at the center of our galaxy, at gravitational waves, and at the black silhouette captured by radio telescopes. After that, we will turn inward to the thermodynamics of horizons, to entropy that scales with area, to Hawking radiation that hints that horizons can glow. With those pieces in hand, we will examine gateways with more care. Wormholes that exist mathematically, but pinch closed too quickly to cross. Traversable wormholes that require exotic matter with negative energy density. Quantum bridges that look like entanglement made geometric. Finally, we will return to your life, to the way this knowledge changes posture and pace, and to the quiet thought that some gateways lead not away from this world, but deeper into it. Let your breath slow. Let the idea of a doorway in the dark take shape and dissolve. The universe is patient. We can be patient with it. The first step is a simple one, almost a footnote in the history of ideas, and yet it already sounds like a whisper from the future. A century before Einstein, a few minds considered a star so compact that even light would not escape. The thought was brief, but the path it marked would one day lead to the black circles that now live in our telescopes. We begin there. In the late 18th century, John Michell in England and Pierre-Simon Laplace in France entertained a striking idea. If light is made of particles that respond to gravity, then a star could, in principle, be massive and compact enough that its escape velocity exceeds the speed of light. Light would rise and then fall back. To distant observers, the star would be dark. Mitchell called it a dark star and imagined how such objects might be detected by their gravitational pull on nearby bodies. It was a clean thought in a Newtonian world, and it faded. Light, in the 19th century, became a wave in an electromagnetic field, not a particle made of mass. The speed of light was elevated from a property to a principle. Gravity was still a force acting in space and time, and the dark star idea felt like a forgotten side path. Then gravity itself changed. Einstein's general theory of relativity in 1915 replaced the notion of a force with the geometry of spacetime. Matter tells spacetime how to curve. Spacetime tells matter how to move. In that geometry, a ray of light follows the straightest possible path, called a null geodesic, through a curved manifold. Solutions to Einstein's field equations describe different gravitational worlds. Only a few months after Einstein published the equations, Carl Schwarzschild, serving at the front in World War I, found the exact solution for the geometry outside a spherically symmetric, non-rotating mass. It contained something odd. At a certain radius, now called the Schwarzschild radius, the mathematical description seemed to fail. At first, many thought this radius was a flaw in the coordinates, a removable inconvenience. It took decades to untangle how much of that oddness was real, and how much was an artifact of the way we were looking. The singularity at the center, where curvature becomes infinite, seemed like a true breakdown of the theory. The strange behavior at the Schwarzschild radius was not. In new coordinates, the radius is smooth, a point of no return rather than a hard wall. From inside that radius, every future path leads inward. Light cannot escape. The event horizon was recognized as a global feature. It is like a sound horizon at a waterfall. Above the drop, you can paddle upstream. Cross a point where the current exceeds your strongest stroke, and all future paths lead down. During the mid-20th century, collapse became a concrete story. J. Robert Oppenheimer and Hartland Snyder calculated the fate of a pressureless ball of dust under its own gravity. It forms an event horizon and continues inward. John Wheeler, always ready to coin a phrase, gave us the words black hole in 1967 after a lecture where he grew tired of longer descriptions. The name stuck, and with it, the modern image. There was resistance, a human kind of hesitation in the face of strange conclusions, but nature did not share that hesitation. Astrophysics found clues that matched the equations. X-ray astronomy, opened by rocket flights and satellites, revealed bright, variable sources in the plane of the Milky Way. In some, a massive visible star orbited an invisible companion that seemed too massive and too compact to be a neutron star. Cygnus X1 became a strong black hole candidate. Over decades, more systems were found. Quasars, the luminous cores of distant galaxies, showed the unmistakable signatures of matter accreting onto supermassive black holes. The energies involved come from gravity. As gas spirals in, it heats through friction and magnetic turbulence and shines at many wavelengths. The jet structures seen in radio and X-rays, long and narrow, hinted at complex dynamics near the horizon where rotation and magnetism conspire. At the center of our galaxy, Sagittarius Asterisk, a compact radio source flickered. Stars nearby traced out orbits over years and decades. Two teams, using infrared telescopes and adaptive optics, tracked those stars and fit their paths. The results were stark. There is a mass of about 4 million suns inside a region smaller than Neptune's orbit. No cluster of ordinary objects would fit. A supermassive black hole sits there. Andrea Ghez and Reinhard Genzel were recognized with a Nobel Prize for their leadership in this ballet of data and patience. And came a different kind of light. Not light at all, but ripples in spacetime called gravitational waves. LIGO, the Laser Interferometer Gravitational Wave Observatory, weighted with arms 4 kilometers long, measuring the distance between mirrors with exquisite precision. In 2015, a brief chirp passed through. 2 black holes had collided more than 1 billion light-years away. Their inspiral and merger rang the detectors in a pattern that matched the predictions of general relativity. Since then, dozens of mergers had been heard. The catalog is full of pairs, some heavy, some light, some spinning, their final tones a tiny hello from extreme gravity. In 2019 and 2022, the Event Horizon Telescope Array gave us images of the shadows of two supermassive black holes, one in M87 and one in our own galaxy. The donut of radio emission, blurred by interstellar scattering and sharpened by careful algorithms, was not a fantasy. It was the expected outline of a photon ring in a shadow, a geometrical consequence of bending light around a deep well. These observations anchor us. They tell us that black holes are not metaphors, not hypothetical. They are as real as the sun, and more common than our first imaginations allowed. This reality gives weight to the thought that they are gateways. If a door exists, it can be touched by light and ring spacetime like a bell. The sky tells us the doors are there. The question is what kind they are. Before we ask about bridges and passages, it helps to kneel at the threshold and study the grain of the wood. The event horizon is the boundary beyond which light cannot return. It is not a surface you could hover just above and feel. It is a mathematical boundary that depends on the entire future of the spacetime. To find it exactly, you would have to know every path of light until the end of time. In practice, physicists use apparent horizons, trapped surfaces that can be located locally from the curvature and the behavior of nearby light rays. For many purposes, that is enough. For intuition, the river analogy is strong. Imagine space as a river flowing toward a waterfall. If the flow is slower than light, a swimmer can paddle outward. If the flow exceeds light speed, even the best swimmer is carried in. The horizon is where the flow matches the swimmer's best effort. A gateway is also a matter of time. If you fall in, you cross the event horizon in finite proper time. You do not see a wall. You do not see a sign that says exit, last chance. You simply notice that all paths forward lead to increasing curvature. For a large black hole, you can linger after crossing the horizon. Tidal forces can be gentle. For a small one, the stretch would be violent, spaghettifying anything with size into long threads. A rotating black hole, described by the Kerr solution, adds new features. There is an ergosphere outside the horizon, where space seems to be dragged around by the rotation. Inside, the structure is richer, with inner horizons where classical instabilities lurk. Rotation opens speculative gateways in the equations, allowing paths that lead to other regions. Nature may close them with turbulence and quantum effects, but the mathematical doors are present, and their very existence is suggestive. Let your senses settle on this picture. A night sky, a faint radio glow, the slow orange of accretion, a silence at the center that is not emptiness, but a rule. Across billions of light years, the same rule repeats, shaping the growth of galaxies, powering jets that seed intergalactic space with magnetic fields and heavy elements. The event horizon is both a boundary and a mirror. It reflects our questions back at us. What is space? What is time? Can information be lost? Can geometry tunnel? We carry those questions with us into the next part, where something surprising happens. A black hole begins to look like a hot object. Horizons begin to have temperature. And the physics of heat and information takes a seat at the table with geometry and light. There is a quiet shift that occurs when we turn from geometry to heat. Black holes were once thought of as perfectly simple cold objects. No hair, in Wheeler's phrase, meaning no distinguishing features besides mass, charge, and spin. Then Jacob Bekenstein asked a question that gently unsettled the tableware. If you drop a cup of tea into a black hole, the entropy of the universe seems to decrease because the tea's microscopic disorder disappears behind a horizon. That would violate the second law of thermodynamics, unless the black hole itself carries entropy. He proposed that the entropy of a black hole is proportional to the area of its event horizon. This idea was bold, because in familiar systems entropy scales with volume, not area. A gas in a box has more entropy if the box is larger, because there are more places to distribute molecules. A black hole's entropy scaling with area suggests that the number of invisible microstates that the hole can be in is counted on its surface, not in its interior. Stephen Hawking supplied the missing constant of proportionality. Using quantum field theory in curved spacetime, he found that black holes should not be perfectly black. Quantum fluctuations near the horizon lead to a slight imbalance in particle creation, and seen from far away, the black hole emits a thermal spectrum with a temperature inversely proportional to its mass. The Bekenstein formula for entropy then becomes precise. The entropy is the area of the horizon divided by 4 in Planck units. This is more than clever arithmetic. It is a guiding star for quantum gravity. It tells us that horizons carry degrees of freedom and that spacetime and thermodynamics are married. It leads to the holographic principle, the idea that the maximum amount of information in a region of space is proportional to the area of its boundary, not its volume. This principle is made concrete in certain versions of string theory, where a universe with gravity is dual to a theory without gravity living on its boundary. It is as if the physics of a room could be entirely described by a painting on the wall, yet the painting would somehow be the room seen another way. The best developed example lives in anti-de Sitter space, a negatively curved arena that is different from our universe, but the conceptual lesson is broad. It suggests that black holes may be gateways not only in literal paths, but in the way they link geometry to information. Hawking radiation raises a paradox. If a black hole evaporates by emitting thermal radiation, and if the radiation is purely thermal, with no imprint of what fell in, then information seems to be lost. Quantum mechanics, as we know it, does not allow that. The evolution of a closed system is unitary, which is a precise way of saying that information is preserved in time. The clash between gravity's horizons and quantum theory's insistence on unitarity is called the black hole information paradox. It has prodded decades of careful thought. Many proposals try to thread the needle. Perhaps information is encoded in subtle correlations among Hawking quanta. Perhaps it is stored in degrees of freedom on or near the horizon. Perhaps space-time extends in ways that we have not fully grasped. One approachable way to feel this is to imagine a library again, the one we used for time. This time the shelves hold the microstates of a black hole. We do not know what they are in detail, but their count is fixed by the area. When you drop in a book, the horizon grows and the library gains shelf space. As the hole shrinks by Hawking radiation, the horizon area decreases. The total number of books must go down if nothing else is going on, which would be a problem if those books carried unique stories that ought not be destroyed. The modern view, informed by calculations of the page curve and quantum extremal surfaces, suggests that the entropy of the radiation first rises, then falls, mirroring unitary behavior, and that islands in the gravitational bulk must be included when we count information in the radiation. The details are technical and gentle, a web of entanglement and extremization, but the message is calm. Information may not be destroyed. It may be rearranged in ways that confuse classical intuition. The membrane paradigm offers a practical model. To a distant observer, a black hole behaves as if it has a thin, hot, electrically conducting membrane at its horizon. This membrane can have currents and vortices. It can have viscosity and resistivity. It is not a real surface, but it is a useful, effective description. The picture serves astrophysics. It helps model how magnetic fields thread near a horizon, and how jets are launched in spinning systems through processes like Blandford-Ziyech. It also helps our imagination. A gateway that behaves like a hot surface is not a cold hole. It is a system with thermodynamic life. The idea of a white hole is a formal time reverse of a black hole. In the equations, a white hole is a region that cannot be entered from the outside, and from which matter can emerge. In the maximally extended Schwarzschild solution, two exterior regions can be connected through an Einstein-Rosen bridge that looks like a wormhole at a single instant. On the other side of the throat sits a white hole region. The bridge, however, is non-traversable. It pinches closed faster than light could cross. It is a beautiful algebraic structure, a geometric knot in spacetime, but it is not a shipping lane. Kerr black holes, which rotate, contain richer interiors that include inner horizons and regions that, in the idealized solution, connect to other universes. These features are likely unstable under small disturbances. Perturbations amplify near inner horizons, a phenomenon called mass inflation, and classical instability tries to close the door. Quantum gravity may alter these conclusions. Loop quantum gravity suggests that singularities are replaced by bounces when spacetime is quantized. The interior of a black hole could collapse to Planck density, then re-expand as a white hole, returning information and matter after a long delay. In this picture, the gateway is temporal. You do not go through to another place. The contents of the collapse come back much later in the same region, softly, like a geyser with a very long cycle. The Planck star idea paints a compact core supported by quantum pressure until it releases. Whether nature uses this mechanism is unsettled, but it is a careful attempt to resolve the singularity without violating known low-energy physics. The scent of gateways floats around these ideas. Some doors are purely mathematical, elegant but sealed by instability. Some are quantum, narrow and subtle, threading information rather than bodies. Some are thermodynamic, leading toward a new view in which spacetime itself is an emergent statistical medium, and the horizon's heat is a clue. Each of these doors is different. It matters that we learn which kinds may exist in nature which are artifacts of idealized symmetry, and which would require engineering that we cannot imagine scaling. Our familiarity with heat and information helps ground these abstractions. You have watched ice melt and tea cool. You have seen that hot things radiate. Hawking told us that black holes are hot in a very precise way. You have stored photos and letters and known that information takes space. Bekenstein told us that a horizon stores information in its area. The stories of heat and information are quietly drawing us toward a newer thought. Perhaps the geometry we live in and the matter that curves it are not separate from the bookkeeping of correlations among microstates. Perhaps black holes are gateways to that bookkeeping. To pass through them is to be folded into the record. Before we reach for more speculative doors and their keys, feel the solidity of what we have. The sky has shown us black holes. Thermodynamics has shown us their heat. Quantum theory has shown us the tension between evaporation and information and a path to reconciliation. Gravity has shown us bridges that are beautiful, but non-traversable in classical form. In the next part, we will explore whether those bridges can be propped open, what energy conditions must be bent, how entanglement might be the thread, and how a signal can be gently ferried through a tunnel that is not a tunnel at all, but a pattern of correlations that we experience as a passage. Imagine a tunnel carved beneath a mountain. You stand at one mouth and speak. Your words travel through air and stone and emerge at the other side. A traversable wormhole would be a space-time version of such a tunnel, a throat that allows signals and perhaps objects to move from one region to another without touching the outside. General relativity allows geometries that look like this, but they are fussy. To keep the throat from collapsing, the stress energy that threads it must violate the usual energy conditions. In simple terms, you need matter with negative energy density in some frame, often called exotic matter. Classical matter does not do this. Quantum fields can, in very controlled ways. The Casimir effect is a well-known instance where quantum fields produce negative energy density between closely spaced conducting plates. The allowed modes of the field are restricted, and the vacuum energy in that region is lower than outside, creating a pressure that pushes the plates together. It is tiny, measurable in precision experiments, and a sign that quantum energy is not always positive. Theoreticians have tried to use effects like this to support wormholes, but nature is stern. Quantum inequalities constrain how much negative energy you can have, how long it can last, and how it must be balanced by positive energy elsewhere. These constraints make it difficult to build and stabilize a macroscopic traversable wormhole that an astronaut could cross, especially in our universe, with its specific matter content and expansion. Yet in a simplified gravitational world called anti-de Sitter space, a clever trio, Gao, Jafferis, and Waugh, found a way to open a wormhole a little. They considered two black holes that share a special quantum entanglement structure, then gently coupled the two boundary theories that describe them. The result is a wormhole that becomes traversable for signals for a brief time. It is not a door you can live in. It is a careful experiment where negative energy induced by the coupling briefly props open the throat, and a message slips through. Even more curious, the process mirrors quantum teleportation, a protocol used in quantum information science to transfer a state from one location to another using entanglement and classical communication. The wormhole is a geometric picture of that process. No superluminal travel occurs. Causality remains intact. The gateway is real in the language of the theory, but it carries only information under strict conditions. This is a new kind of door. It is not a hole in space. It is a hollow made in the web of correlations. Juan Maldacena and Leonard Susskind proposed a bold unifying idea encoded in a short, memorable equation. A equals EPR. A refers to Einstein-Rosen bridges, wormholes in the geometry of general relativity. EPR refers to Einstein-Podolsky-Rosen entanglement in quantum mechanics. The suggestion is that a pair of maximally entangled black holes might be connected by a non-traversable wormhole, and more generally, that entanglement and spatial connectivity are two faces of one thing. Spacetime might be the large-scale image of an underlying network of entangled degrees of freedom, like a quilt whose pattern is determined by how its threads cross. If this is correct, the strongest gateways in the cosmos are not pipes, they are relationships. The geography of the universe would be a map of correlations. If entanglement stitches space, then a black hole could be a knot in the stitching. Black hole interiors might be mirrors of their exteriors, extended through entanglement that hides behind the horizon. Paradoxes at the horizon, like the proposed firewall, ask whether an infalling observer would be burned by high-energy quanta that form when exterior modes are entangled with Hawking radiation far away. The tension among three principles, the smoothness of space-time at the horizon, the purity of the radiation, and the normal laws of quantum mechanics, is sometimes called the Ampere's problem. Many physicists suspect that quantum gravity resolves the tension by adjusting our bookkeeping of what belongs to what, not by literally burning the traveler. The modern page curve calculations, with islands that jump inside the horizon to become part of the radiation's entanglement wedge, hint at a quiet resolution. The horizon remains smooth for infallers. The exterior description claims ownership of more of the interior than classical geometry would grant, through the subtle logic of extremal surfaces. Loop quantum gravity carries its own quiet proposal. If space-time has a discrete structure at the Planck scale, singularities can be avoided. Collapsing matter may reach a maximum curvature, then rebound. The exterior would see a very long delay because of gravitational time dilation near the horizon. The interior would experience a brief compress and bounce. The white hole that emerges could be tiny, releasing the stored matter in a slow drizzle across ages. This would make a black hole a gateway in time, a delayed mirror, transforming collapse into return. Astrophysical constraints limit how often such events can light the sky, but the idea offers a specific mechanism for how nature could heal a wound in the equations with minimal surgery. Astrophysical gateways exist in another sense. The neighborhood of a spinning black hole is a place where energy can be extracted from rotation. The Penrose process shows that trajectories inside the ergosphere can split in such a way that one piece falls into the hole with negative energy relative to infinity, while the other escapes with more energy than it had. In practice, Magnetic fields and plasma do the work, threading the ergosphere and launching relativistic jets. These jets propagate out of galaxies and seed the intergalactic medium with fields and heavy particles. Black holes are therefore gateways for energy, from rotation into structure across scales. They are not mere sinks. They are engines. All of these doorways rest on habits of careful thought. Energy conditions, entanglement, causal structure, thermodynamics, quantum inequalities, and symmetry. It is easy to imagine a portal that ignores these, but our aim is different. Our aim is to learn the shape of what could be, given what is known. We find that nature is generous with beauty, but strict with passage. Traversable wormholes are not ruled out in all contexts, but in realistic settings, they require exotic features that we have not seen in the wild. Non-traversable bridges are common in the equations and useful as pictures. Quantum teleportation through an ADS-E wormhole is a profound metaphor that is also a theorem in its own playground. Bounces that turn black holes into white holes are promising ideas that must face the sky's data. The gateway that is certain is the doorway to unification. Black holes force conversations between fields that used to sit at separate tables. Let analogies help gently. When you hold two ends of a ribbon and twist, a loop appears. If you stitch many ribbons together and twist them in patterns, the surface that results can be connected in ways that your fingers feel before your words catch up. Entanglement feels like such stitching, except that the threads are relationships among quantum states, and the surface is the geometry of space. A wormhole, in this analogy, is a place where many stitches align to make a short path through an otherwise long route. If the stitches slip, the hole closes. If the fabric is stretched, the hole narrows. If the pattern is paired with a precise tempo of coupling, a message can be sent through the seam. This is a human picture, not a derivation, but it allows a feeling for why negative energy, coupling, and timing matter. We can also stay close to the sky. A photon ring around a shadow, a star whipping around an invisible mass. A chirp that lasted a fraction of a second, crossing 1 billion years to shake a mirror on Earth. These are doors that have already opened, not to another universe, but to precision. Through them we have walked, and in the new room we find questions hanging like mobiles from the ceiling. Can a horizon store a memory? How does a quantum state know to smear across a surface? Is spacetime an average, like temperature, arising from many small constituents? If so, black holes are furnaces where those constituents reveal their collective behavior. We are not done. One more room waits, a softer one, where we ask what these gateways mean for us. Not for travel, not for escape, but for posture. What does it change to know that the most extreme objects in nature are also the most informative? That in the deepest dark, the laws write in clear script. We step there next. You are here in a particular evening or morning, listening with your own rhythms, while somewhere in the halo of the Milky Way, two black holes are spiraling together in silence that only spacetime can hear. The notion of gateways may have shifted a little for you. Perhaps it is less about stepping through a door into a parallel world, and more about learning what kinds of doors the world makes on its own. The event horizon is a one-way threshold for light. The thermodynamic surface is a record keeper. The wormhole is a shape and geometry that needs unusual scaffolding to stay open. The white hole is a mirror image that may be a rare natural act or a cognitive model of how singularities are mended. Each speaks in its register, and together they hum. In practical life, this knowledge rarely asks anything of you. Your coffee cools, your days pass. Your devices do their quiet work, some guided by algorithms that owe their lineage to the same physics that tames the chaos near horizons. Yet there is a posture that can come from living with the thought that the universe stores its secrets in the same places it makes its engines. You can carry a kind of patience into your work, a willingness to stand at thresholds without forcing them, to learn the hinges and the grain before pushing. You can let go of a little of the need for shocking novelty, and instead cultivate a deeper appreciation for clarity, the way a proof does not need fireworks to be beautiful. Black holes as gateways to understanding means that mystery is not an alternative to method. The most mind-bending ideas in this landscape were earned the slow way. They came from equations complemented by observation and by the refusal to look away when two principles seem to clash. In your own days, that can translate into a gentler way of holding contradictions. You can let opposites sit and keep asking what larger pattern contains them both. Gravity and quantum mechanics seem opposed at the horizon, yet their conversation is leading to holography, to islands, to a new map of information. In life, urgency and rest often feel opposed, yet a calm focus can hold them together. You are allowed to work slowly on something that matters. Gateways can also mean gratitude for boundaries. The event horizon is a limit, and it sharpens things. It creates a region of the universe where causality takes a specific shape, where notions like no hair and area, increased theorems take hold. Constraints are not only restrictions, they define what is possible. The black hole's inability to radiate classically makes Hawking radiation significant when quantum effects are included. A door that will not open teaches you the value of the key that finally fits and what it took to cut it. The idea that entanglement might be the stitching that becomes space has a gentle echo in human life. The most meaningful passages you have made were likely opened by relationships. A mentor, a friend, a small community, each a thread that crossed another thread until a path appeared. The path was not a shortcut through physics. It was a shortcut through confusion, a thread of connection that shortened the distance between your now and a new understanding. That is the same pattern, drawn in soft light instead of plank light. It invites a little awe. The universe may be relational all the way down, from neurons that synchronize to black holes that share a quantum state across a horizon. If black holes are gateways in time, as loop quantum gravity suggests, there is a poetic solace that you can carry without needing to swear to the mechanism. Things that fall may return changed. Loss may have a long cycle. Information that feels lost may be preserved in ways you cannot yet decode. Hawking radiation is slow, but it is relentless. It does not erase what the black hole has been. It writes it in a different script. That image can be companionable when you try to make sense of memories and futures that are not yet clear. Look up if it is night where you are. The sky is not quiet because nothing happens. It is quiet because the happenings are in scale with the calm. Photons launched millions or billions of years ago are arriving now, not in a hurry, simply keeping their appointments set by the speed they must travel. Somewhere far away, a jet from a black hole's pole is inscribing a line across intergalactic space that will last longer than the history of our species. Somewhere closer, stars are threading past the center of our galaxy, turning a slow, old wheel. These are spaces where gateways are not disasters. They are durable features, patient openings that do not scold us for being small. If you travel someday to a black hole in your imagination, take a compass of concepts. Know that event horizons are global, not pinnable with a tack. Know that Hawking radiation is a quantum glow, faint unless the black hole is tiny. Know that non-traversable bridges exist easily in equations, and that traversable ones are scarce, fragile, and dependent on precise conditions. Know that information is not a ghost. It is a measurable, countable thing that physics treats seriously, and that black holes treat with paradoxical respect. Then return, as most journeys require, to your porch or your pillow. Bring back patience and a little wonder. Thank you for spending this quiet time with Hypnosphere, for listening to a story about doors that the universe makes in the dark. If you would like more calm science journeys, you are warmly invited to subscribe. There is no urgency. We will be here when you come back, reading the stars at an easy pace, listening for the soft logic that turns mysteries into gateways.